Now let's talk about the applications of the Gouy Stodola equation. Now if you remember, the equation was that the work lost due to the irreversibility is equal to T naught, that is the the temperature of the surroundings, into the rate of entropy generation. So this was the Gouy Stodola equation. Now in this application, or this is the first application of this equation, and we will talk about the heat transfer through a finite temperature difference. Now if you look at this diagram over here, okay, in this what is happening, heat transfer Q dot, it occurs from hot reservoir T1, okay, to the cold reservoir T2. So during this transaction of heat from hot reservoir to cold reservoir, if you talk about the entropy generation, that is S gen, so in this the reservoir at T2 is gaining heat, so you would have plus Q dot upon T2, and the reservoir at T2 is losing heat, so you will have minus Q dot upon T1. Okay, so if you solve it, you would get Q dot into T1 minus T2 upon T1 T2. So this is the value of entropy generation, or the rate of entropy generation, I would say. Now if you were to find out the value of the work lost, or the rate of work loss due to the irreversibility and due to this heat transfer between these two finite temperature limits. So if you look at this equation given by Gouy Stodola, this is equal to the surrounding temperature into the rate of entropy generation. Now in this particular case, the surrounding temperature is T2, so this will become T2 into the rate of entropy generation. So if you put this value over here, you will get, let me move it a bit further, so you will get W lost is equal to Q dot into T1 minus T2 upon T1. So this is the value of the work lost in this case. Okay, now if you look at this diagram, now what is happening in this diagram, if now the heat transfer Q dot that takes place from T1 to T2, now it is taking place through a reversible heat engine. So this is the reversible heat engine, placed between the two temperature reservoirs T1 and T2. Okay, the entire work output from this reversible heat engine is dissipated in this break. Okay, so the entire work is taken in this break, from which an equal amount of heat is rejected to the reservoir at T2. So whatever work that comes out of the engine, that is W dot, that goes into this break, and an equal amount of heat that is equal to W dot is now rejected to the reservoir at T2. So this means that heat transfer through a finite temperature difference is equivalent to the destruction of its availability. Now after this, let's look at the second application. So the second application is the flow with friction. Flow with friction. Okay, so let us draw a diagram to analyze this. So I think the first application is clear, that is, whenever there is a heat transfer through a finite temperature difference, there is some work loss, so there is some irreversibility. Okay, and let's now move to the second application. So let us draw a steady and adiabatic flow of an ideal gas. So let us say you have such a pipeline or any passage through which an ideal gas is flowing, and this passage or this pathway is insulated so that the process stays adiabatic, and we would assume steady flow as well. So let us say this section is section 1 and this section is section 2. The pressure at section 1 is P1 and the pressure at section 2 is P2. Alright, so the flow is from section 1 towards section 2. So the flow that is taking place is steady and adiabatic. So the flow is steady and adiabatic. Alright, now if you apply the first law by the application of steady flow energy equation in the first law of thermodynamics, in such a case the enthalpy at section 1 would be equal to enthalpy at section 2. So this would be your SFE for this particular application, isn't it? Because the velocity heads will be equal, there is no change of area. The potential heads would be different, or would be same, not different but same. Okay. There is no heat loss because it is adiabatic, and there is no shaft work involved. Okay, so this is also equal to 0. So the only thing that is left is the enthalpy. So at both these sections the enthalpy would be the same. Okay, now if you apply the second law, so by second law, now by second law you can write that T ds, this is equal to dH minus VdP. Now why did we write this particular equation? So if you remember the concept where we talked about the first and the second laws combined, this was the equation that can be used for any process. Okay, so this is the application of second law by combining it with first law. Now if you bring this t towards the right hand side and divide it with all the terms, so you would get ds is equal to dH upon t minus V upon t into dP. Now because the process is taking place from 1 to 2, I can integrate this from state 1 to state 2. So for the entropy, it would become integral 1 to 2 ds is equal to, I can write down integral from state 1 to state 2 dH upon t minus, okay, so you can write integral state 1 to state 2 V upon t into dP. Alright. So now if you look at the first law, that is the enthalpy at both the sections is same, so you can strike off this thing because dH is 0. Okay, and because it's an ideal gas, so I can apply PV is equal to mRT. Now in this case I will take the mass flow rate, so the value of V upon T can be easily written as m dot R upon P. So V upon T can be replaced by mR upon P. So this is nothing but the entropy generation. Alright, and this becomes minus integral 1 to 2 m dot into R into dP upon P. So this is what you get. Now if you integrate it, because the integration is between or is for the variable P, so I'll write down the limits are from P1 to P2, so this would become minus m dot R into natural log of P2 upon P1. Now if you look at this, so P2 is the pressure at section 2. Now whenever there is a pipe, or whenever there is a pipe flow, alright, and the pipe flow has some friction, so there will be some pressure loss at the section number 2. So I can say that P2 is nothing but P1 minus a little bit of pressure drop. So P1 minus delta P is the value of P2, that is the pressure at section 2. So let's replace P2 in this particular equation by this expression. So we would get S dot gen is equal to minus m dot R into natural log of P1 minus delta P upon P1. So this can be further written as minus m dot R natural log 1 minus delta P upon P1. Okay, so now if you look at this, if you recall the expression of 1 minus x, log of 1 minus x, and if you expand this up till the first term only, so you will get 1 minus x only. So this equation would now become, let's use some other color, so it will become, no, the wrong one, let's use green color, so it will become entropy generation rate is equal to minus m dot r into 1 minus delta P upon P1. So this is what you would get. And if you talk about this expression and say that the value of x is less than 1, then log 1 minus x is almost equal to minus x. Okay, so this can be written as minus m dot r, not log, no, log is gone, minus delta P upon P1. So the value of entropy generation rate is now is equal to plus m dot into r into delta P upon P1. So this is the expression we need to remember. Now if you talk about the work lost, okay, so the rate of loss of work, now this is equal to the difference between the Keenan functions. So you will have B1 minus B2 because the flow that we are taking is a steady flow, and this is equal to m dot into, for the section 1 the Keenan function would be h1 minus t naught into s1 minus h2 minus t naught into s2. Okay, now we know that the h1 and h2 are same, so they'll cancel off. So the only thing that will be left is m dot into t naught into s2 minus s1. So this is what you are left with. Okay, and if you look at this part, this is nothing but the entropy generation rate. Okay, and the entropy generation rate from our analysis is the value or the expression which is m dot r into delta P upon P1. So the value of the work lost in case of a flow with friction is equal to T naught into m dot r into delta P upon P1. So this is the value of work lost in a flow with friction. So this means that the decrease in availability or the lost work is proportional to the pressure drop delta P and the mass flow rate m dot. Alright, so this can also be illustrated with the help of a diagram which is called a Grassmann diagram. So let's draw that diagram. It is Grassmann diagram. Okay, so let us draw a flow which is represented in such a manner. Okay, so this is what you have, and yeah, so this is the flow which is represented. Alright, so this width is the available energy, or you can say the total input energy. So this is where the mass input is there. So you have some mass inflow, the rate of mass inflow. Alright, now what happens is as the flow has some friction, alright, there is some work that is lost. So let us say this is the work that is lost. So I would say W dot lost. So because there is some energy lost in terms of the availability, so the mass flow rate at the outlet would be a little less. So this width is higher as compared to this width. So this difference in the width It is proportional to the availability of the stream. Alright, so this is how you can represent the decrease in the availability or the lost work in case of a flow with friction. So I hope you understood the concept of the Gouy Stodola equation and the applications of this equation. Now, after this, let's go on to the next video and talk about second law efficiency.